The National Electrical Code (NEC) allows for the use of the 90°C column for conductor sizing in specific scenarios involving load diversification. Diversification happens when several loads are connected to the same service, and their usage patterns do not significantly overlap. Considering 6 disconnects, the rationale is that the chance of all 6 switches being fully energized at the same time is extremely low. Therefore, the peak current demand on the service entrance conductors is reduced, allowing for smaller conductors selected from the 90°C column. While the concept of diversification is valid, using the 90°C column for service entrance conductors in this situation raises several questions. Firstly, is the diversification claim valid? The probability of all 6 switches being on simultaneously depends on the specific load types and usage patterns, which can vary widely. Secondly, is the reduced peak demand significant enough? Even if diversification occurs, the magnitude of the peak demand reduction must be substantial to justify using the 90°C column. Thirdly, does the NEC support this approach? The NEC does not explicitly address the use of the 90°C column for service entrance conductors in this case. A recommended approach is to use the 75°C column for sizing service entrance conductors unless there is clear evidence of significant load diversification and reduced peak demand, until this practice is further clarified through industry consensus or court interpretations. Firstly, the use of the 90°C column can only be applied to the service entrance conductors and not to the service equipment itself. Secondly, the safety of the installation should always be the primary concern, regardless of the sizing method used. Thirdly, it is essential to document the basis for any deviations from the NEC requirements and obtain approval from the authority having jurisdiction. When dealing with service entrance conductors and their sizing, one must adhere to the National Electrical Code (NEC), which provides guidelines for safe and effective electrical installations. The NEC outlines requirements for conductor ampacity, temperature ratings, and termination methods to ensure the reliability and safety of electrical systems. In many cases, the NEC specifies the use of the 75°C ampacity column for determining the allowable current carrying capacity of conductors used in service entrances. This is because service equipment terminations are typically rated for 75°C, as indicated in NEC section 110.14. C. However, there are situations where engineers may consider using the 90°C ampacity column for sizing service entrance conductors. This practice is often justified by the concept of load diversification, where multiple loads connected to the same service are unlikely to operate at their maximum demand simultaneously. Load diversification can result in a lower overall peak demand on the service entrance conductors, potentially allowing for the use of smaller conductors selected from the 90°C column. When evaluating the use of the 90°C ampacity column for service entrance conductors, several factors must be considered. Firstly, the validity of the load diversification claim should be carefully assessed. The probability of all connected loads operating at their maximum demand simultaneously depends on the specific types of loads and their usage patterns. If the loads are highly correlated or tend to operate concurrently, the load diversification benefit may be minimal. Secondly, the magnitude of the peak demand reduction resulting from load diversification must be significant enough to justify the use of the 90°C ampacity column. The reduction in peak demand should be substantial enough to ensure that the service entrance conductors are not overloaded under normal operating conditions. Thirdly, the NEC does not explicitly address the use of the 90°C ampacity column for service entrance conductors based on load diversification alone. Therefore, it is essential to consult with the authority having jurisdiction (OJ) and obtain their approval before deviating from the standard practice of using the 75°C ampacity column. In addition to these considerations, the temperature ratings of the service equipment terminations must also be taken into account. As mentioned earlier, service equipment terminations are typically rated for 75°C. Therefore, even if the 90°C ampacity column is used for sizing the service entrance conductors, the conductors must still be terminated in equipment rated for 75 degrees Celsius or higher. To ensure compliance with the NEC and maintain the safety and reliability of the electrical installation, it is recommended to follow these guidelines. Firstly, conduct a thorough load analysis to determine the expected peak demand on the service entrance conductors, taking into account load diversification. Secondly, consult with the AHJ to discuss the proposed use of the 90 degrees Celsius ampacity column and obtain their approval. Thirdly, ensure that the service equipment terminations are rated for at least 75 degrees Celsius. Fourthly, properly document the basis for using the 90 degrees Celsius ampacity column, including the load analysis and AHJ approval. Fifthly, install the service entrance conductors in accordance with the NEC requirements, including proper rating for ambient temperature and conduit fill. Sixthly, perform regular inspections and maintenance to ensure that the electrical installation continues to operate safely and reliably. By following these guidelines, electrical contractors can make informed decisions about sizing service entrance conductors and ensure compliance with the NEC while maintaining the safety and reliability of the electrical system. When engineers propose sizing service entrance conductors using the 90 degrees Celsius column based on the diversification of 6 disconnects, several critical factors must be carefully evaluated. The concept hinges on the assumption that not all 6 disconnects will be fully energized simultaneously, reducing the peak current demand on the service entrance conductors. However, this approach necessitates a thorough understanding of load characteristics, NEC guidelines, and potential safety implications. Firstly, it's crucial to validate the diversification claim. The likelihood of all 6 switches being on at once depends heavily on the types of loads connected and their usage patterns. If the loads are independent and have diverse operating schedules, the assumption might hold. However, if the loads are interdependent or tend to operate concurrently, the diversification benefit could be minimal. A detailed load analysis is essential to determine the actual demand profile. Secondly, even if diversification exists, the reduced peak demand must be significant enough to justify using the 90 degrees Celsius column. The ampacity of conductors must always be sufficient to handle the maximum expected current. Using the 90 degrees Celsius column allows for smaller conductors, but only if the reduced peak demand is substantial and well documented. Engineering calculations must demonstrate that the conductors will not be overloaded under any foreseeable operating condition. Thirdly, the NEC doesn't explicitly endorse using the 90 degrees Celsius column for service entrance conductors solely based on diversification. While the code allows for ampacity adjustments based on specific conditions, it emphasizes safety and adherence to termination temperature ratings. Service equipment terminations are typically rated for 75 degrees Celsius, as per NEC section 110.14. C. Using conductors sized from the 90 degrees Celsius column might necessitate special considerations to ensure that the termination temperature limits are not exceeded. Fourthly, it's imperative to prioritize safety above all else. The NEC provides minimum requirements for electrical installations, and any deviation from these standards must be thoroughly justified and approved by the authority having jurisdiction. The safety of the installation should never be compromised for cost savings or convenience. Factors such as ambient temperature, conductor bundling, and voltage drop must be carefully considered to ensure that the electrical system operates safely and reliably. Fifthly, thorough documentation is essential. Any deviation from standard NEC practices must be meticulously documented, including the load analysis, engineering calculations, and justifications for using the 90 degrees Celsius column. This documentation should be submitted to the AHJ for review and approval. The documentation should also include details of the conductor and termination specifications, as well as any special installation requirements. In summary, while the concept of using the 90 degrees Celsius column for service entrance conductors based on load diversification might seem appealing, it requires careful evaluation, thorough analysis, and strict adherence to safety standards. Electrical contractors should always consult with qualified engineers and the AHJ before implementing such practices. The decision to use the 90°C column should be based on sound engineering judgment and a comprehensive understanding of the electrical system and its operating characteristics. In electrical engineering, the sizing of service entrance conductors is a critical task that requires careful consideration of various factors, including load characteristics, ambient temperature, and applicable codes and standards. The National Electrical Code, NEC, provides guidelines for determining the appropriate conductor size to ensure the safe and reliable operation of electrical systems. When sizing service entrance conductors, engineers typically refer to ampacity tables in NEC, which specify the allowable current carrying capacity of conductors based on their insulation type and temperature rating. Conductors with high temperature ratings, such as those rated for 90°C, generally have higher ampacities than conductors with lower temperature ratings, such as those rated for 75°C. However, the NEC also imposes limitations on the use of conductors with higher temperature ratings, particularly in service entrance applications. One such limitation is that service equipment terminations are typically rated for 75°C, as specified in NEC section 110.14. C. This means that even if a conductor is rated for 90°C, it must be terminated in equipment that is rated for 75°C or higher. Therefore, the ampacity of the conductor must be derated to match the temperature rating of the termination. In some cases, engineers may consider using the 90°C ampacity column for sizing service entrance conductors based on the concept of load diversification. Load diversification refers to the fact that not all electrical loads in a building or facility operate at their maximum demand simultaneously. By taking load diversification into account, engineers can potentially reduce the size of the service entrance conductors, resulting in cost savings and other benefits. However, the use of the 90°C ampacity column for service entrance conductors based on load diversification is not explicitly addressed in the NEC. Therefore, it is important to carefully evaluate the specific circumstances of each installation and consult with the authority having jurisdiction (OJ) before implementing this approach. When evaluating the use of the 90°C ampacity column for service entrance conductors, engineers should consider the following factors. Firstly, the validity of the load diversification claim should be thoroughly assessed. This involves analyzing the types of loads served by the service entrance conductors and determining the likelihood that all of these loads will operate at their maximum demand simultaneously. If the loads are highly correlated or tend to operate concurrently, the load diversification benefit may be minimal. Secondly, the magnitude of the peak demand reduction resulting from load diversification must be significant enough to justify the use of the 90°C ampacity column. The reduction in peak demand should be substantial enough to ensure that the service entrance conductors are not overloaded under normal operating conditions. Thirdly, the temperature ratings of the service equipment terminations must be taken into account. As mentioned earlier, service equipment terminations are typically rated for 75°C. Therefore, even if the 90°C ampacity column is used for sizing the service entrance conductors, the conductors must still be terminated in equipment rated for 75°C or higher. Fourthly, the AHJ should be consulted to determine whether the proposed use of the 90°C ampacity column is acceptable. The AHJ may have specific requirements or guidelines that must be followed in order to obtain approval for this approach. In addition to these factors, engineers should also consider the potential impact of future load growth on the service entrance conductors. If the building or facility is expected to experience significant load growth in the future, it may be prudent to size the service entrance conductors based on the anticipated future load rather than the current load. The practice of using the 90°C column for sizing service entrance conductors based on the diversification of 6 disconnects raises several important considerations within the framework of the National Electrical Code, NEC. While the NEC does not explicitly prohibit this practice, it does not explicitly endorse it either, making it crucial to evaluate the specific circumstances and potential implications. Firstly, the validity of the load diversification claim is paramount. The assumption that not all 6 disconnects will be fully energized simultaneously needs rigorous justification. This requires a detailed load analysis that considers the types of loads connected to each disconnect, their individual duty cycles, and the probability of concurrent operation. If the loads are diverse and their operation is staggered, the diversification factor may be significant. However, if the loads are interdependent or tend to operate in unison, the diversification benefit may be minimal. Secondly, even if a valid load diversification exists, the magnitude of the peak demand reduction must be substantial enough to warrant the use of the 90°C column. The ampacity of the service entrance conductors must still be adequate to handle the maximum anticipated current, taking into account any applicable derating factors for ambient temperature, conductor bundling, and other conditions. Engineering calculation should demonstrate that the conductors will not be overloaded under any foreseeable operating scenario. Thirdly, NEC Section 110.14 C stipulates that equipment terminations are generally rated for 75°C. This means that even if the 90°C column is used for conductor sizing, the conductors must be terminated in equipment rated for 75°C or higher. This requirement may necessitate the use of larger conductors than would otherwise be required based on the 90°C ampacity, or the use of termination methods that are specifically designed to accommodate high temperature conductors. Fourthly, the authority having jurisdiction plays a critical role in the approval process. The AHJ has the final say in whether or not the proposed design meets the requirements of the NEC and is safe for installation. It is essential to consult with the AHJ early in the design process to discuss the proposed use of the 90°C column and to obtain their approval. The AHJ may require additional documentation such as load calculations and engineering analyses to support the design. Fifthly, documentation is crucial. All assumptions, calculations, and justifications for using the 90°C column must be clearly and thoroughly documented. This documentation should include a detailed load analysis, conductor ampacity calculations, termination temperature ratings, and any other relevant information. The documentation should be readily available for review by the AHJ and other stakeholders. In summary, while the use of the 90°C column for sizing service entrance conductors based on the diversification of 6 disconnects may be permissible under certain circumstances, it requires careful evaluation, thorough analysis, and strict adherence to the requirements of the NEC. It is essential to consult with qualified engineers and the AHJ to ensure that the design is safe, reliable, and compliant with all applicable codes and standards. The decision to use the 90°C column should be based on sound engineering judgment and a comprehensive understanding of the electrical system and its operating characteristics.